Hello viewers, I'm Kausalya. Today we are going to discuss about reluctance and series and parallel magnetic circuits. So first we start with reluctance. So here regarding reluctance, again we are going to consider the same structure, that is a ferromagnetic ring, and it has n turns, and to the n turns we are supplying a current of I amps. Now, again, the circumference of the ring is considered as L meters and the cross-sectional area is taken as A meter square. So, these are all the things, that is the same ferromagnetic ring is considered for our previous discussions also. You see, again, this is the ferromagnetic ring which we are going to consider to discuss about reluctance also. Right. So, here this is a ring. Okay, it has some n turns of coil and a current I amps is allowed to flow through it. And here the total circumference of the ring, it is measured in terms of meters. Right, just we are taking a thread and we are measuring the length. So now you see the main circumference is L meter and the cross-sectional area is A meter square. So the flux is given by the formula. The flux is given by B into A. Right. So again the formula for B is mu naught mu r h. We will generally tell it as mu h, and mu is nothing but mu naught mu r. So B is equal to mu naught mu r h, and we are substituting this value here. So the equation for pi becomes mu naught mu r h into A. Right. And here what is the formula for the magnetizing force? So here it is given by, the magnetizing force is given by F by L. So here in this case again you see the value of pi, we are replacing H by F by L. So here the expression becomes mu naught mu r F by L into A. So finally we are just rearranging the above equation. Right. We are keeping F only in numerator and we are rearranging these terms. So here when you write, here it becomes L by mu naught mu r A. So L by mu naught mu r A can be replaced by a single term. It is known as R. This R is nothing but reluctance. Right. So pi is given by F by R. So here R is the reluctance of the magnetic circuit, and again you see when you rearrange this expression, pi is equal to F by R, we are writing R. Okay, we are going to write an expression for R. Therefore R is nothing but F by pi ampere terms per Weber, where R is nothing but L by mu naught mu R A. So here R is nothing but it is the ratio of L by A. Right. So L is nothing but the circumference of the ring and A is the cross-sectional area. So the reciprocal of reluctance is called by the term permeance. Right. The reciprocal of reluctance is permeance. So for a given magnetic circuit, you see the reluctance R is a constant because R depends upon L, A and mu naught mu r. You see the length of the circumference is always fixed. Similarly, the area of the ferromagnetic material is always fixed. That's why here we are calling the value of R as constant. And again, depending upon the material, the value of mu r also remains the same. Yes or no? So that's the reason why here we are calling the value of reluctance as a constant. So for a given magnetic circuit, the reluctance R is a constant and its value depends on the geometrical dimensions. What do you mean by geometrical dimensions here? Again, the length of the circumference and area of the material. Right, area of the core and permeability of the magnetic circuit. Okay, this is what just I said now. And finally, you see the flux produced, because here we are framing an expression, right? Pi is equal to F by R. So here you see the flux produced in a circuit is directly proportional to the magnetomotive force, and this is a basic concept which we seen in our previous video. So to replace this proportionality, here we are including a constant. Okay, constant into MMF. So what is this constant? This constant is nothing but reluctance. Okay, reciprocal of reluctance, 1 by reluctance into MMF. So finally the flux produced in a magnetic circuit is equal to MMF by reluctance. So next we are going to discuss about magnetic circuit computations. That is, we are going to discuss about a series magnetic circuit and parallel magnetic circuit. So here regarding a series magnetic circuit, you see as the name indicates, here we are having materials of materials, you see, a closed magnetic path. As we all know, the flux will flow only in a closed magnetic path. Right. So a closed magnetic path consisting of different sections of varying permeabilities and physical dimensions but having the same magnetic flux is called a series magnetic circuit. Here when you read by definitions, you may feel a bit confused, but I'll make it clear. You see here we are having three different materials, right? You see this part, okay, this part forms one, and here this part forms other one, and here this part forms the third one. So here we are having different materials, and all these three materials have different permeabilities, right? And also when you look at the dimensions, they don't have the same dimension, okay? Here you see the area is minimum, whereas here the area is broader. But though they vary in their permeabilities and physical dimensions, the flux flowing through this path remains the same. For example, here if a flux of 10 flows through this path, again the same value of 10 flows through this path also, right? So whenever in a closed magnetic path, the value of flux remains constant irrespective of the permeabilities and physical dimensions, then that circuit is known as series magnetic circuit, right? So here now we are going to give an explanation about the diagram here. So the figure shows a closed magnetic circuit consisting of three magnetic cores, right? So this is one part, and this is the second part, and this is your third part. So here their lengths are L1, L2 and L3, and their cross-sectional areas are A1, A2 and A3. And the value of their absolute permeability, okay, it is given by mu1, mu2 and mu3. Right, they have different area, they have different length, and they have different permeabilities. Apart from that, you see when you look at this diagram, here we have two coils, and the two coils are provided with two different currents, namely I1 and I2. Right, so only when a conductor carries current around a magnetic core, that produces flux, right? That flux is produced due to the magnetizing force. So here we have two coils, right? Therefore, two magnetic forces are produced here. So that is what indicated here. One is F1 and here it is F2. Right, and again depending upon the direction of the current that flows through the coil, here we are assigning the symbol as plus and minus, right? So again you see here we are having three cores, right? Therefore three resistors are present. So here it is represented as, you see, so this is your F1, right, which is N1, which is a product of N1 I1. So here R3 and again here R1, and here I have this F2, that is N2 into I2, and here it is R2. Right, so R3, R1 and R2 are represented as resistors in this equivalent circuit. Now here we have two MMFs, right? You see here the current enters by this direction, but whereas here current enters by this direction, okay? That is, the direction is not same, they are opposite. That's why here it is represented as a plus and on the top, and here plus at the bottom, right? So now we are going to calculate the value of total MMF. So here the total MMF is given by addition of, okay, we are adding F1 and F2. So F1 plus F2. So here F1 is nothing but N1 I1 and F2 is N2 I2, and here instead of writing plus, we are writing it as plus or minus, because here the flux is produced due to the 2 MMF, because here we have 2 MMF produced, right? One is produced by this coil and the second MMF is produced by this coil. So here the MMF produced will be additive, okay? We can add the MMF produced by these two coils when the MMF produced, okay, when the flux produced are in the same direction. Suppose if the flux produced are in the opposite direction, then we have to subtract, right? So that's the reason here why the entire value, that is the total value of MMF, is given by N1 I1 plus or minus N2 I2, right? And you see the MMF produced depends, again the MMF depends upon the direction of the winding of the coils as well as the direction of the current. So anyway, finally a flux is produced in a series magnetic circuit. So the flux produces, this flux produces a magnetic potential drop, yes or no? Because whenever a flux flows through a core, it produces some drop. So this magnetic potential drop is produced in three portions of the core, because here we have a core made up of three different materials. So obviously it will produce us three different magnetic potential drop. So here the magnetic potential drop is given by, that is, it is a summation of m1 plus m2 plus m3. So this potential drop is nothing but it is h1 into I1. Here m2 is h2 I2 and m3 is h3 and sorry, this is L1. H1 L1, H2 L2 and H3 L3. So here in this case H is nothing but it is the ratio of B by mu. So here it is B1 by mu1 and here B2 by mu2 and here B3 by mu3. Now just we are multiplying both the numerator and denominator terms by A1, A2 and A3. Okay, just to have a simplified form. So here we are multiplying and dividing by A1 and here by A2 and here by A3. So and finally you see pi 1, it is nothing but B1 A1 which is equal to B2 A2 which is equal to B3 A3, because you see here the flux produced is same. Okay, that is the reason. So here we can rearrange, that is we can rename B1 A1, B2 A2 and B3 A3, all are same because the flux produced in a series magnetic circuit is same. So now we can replace this B1 A1, B2 A2 and B3 A3 by pi. So here you see we are replacing that. So B1 A1 is replaced by pi, and what is this L by A? That is the ratio of L by A is nothing but reluctance, right? So this L1 by A1 mu1 is replaced by R1, and here this L2 by A2 mu2 by R2 and L3 by A3 mu3 by R3. Right? So finally when you add all these values, we are simply representing this as R, right? So R is nothing but it is R1 plus R2 plus R3. Again you see this H1, H2, H3 denotes the magnetic field strength, and B1, B2, B3 denotes the flux densities, and R1, R2, R3 it tells the reluctance, right? So here this equation A represents that for a series magnetic circuit, the total reluctance of the magnetic circuit is the summation of the individual reluctances of the different portions of the circuit. This is true, right? Because the flux produced is same because it is a series magnetic circuit, and again the total value of reluctance is nothing but it is a summation of the reluctances of the individual part of the different materials. So that's all about series magnetic circuit. Now we move to the parallel magnetic circuits. So regarding parallel magnetic circuit, again the same thing here. You see there is a magnetic core. Okay, the flux is produced in the core due to the magnetomotive force. Okay, and but this magnetomotive force, you see, acting in a magnetic circuit gets divided into two or more branches of the magnetic core. So the fluxes in these branches may be different, but the magnetic potential drop across the branches remains the same. Okay, this is known as parallel magnetic circuit. So here in this case, it is clearly given that the magnetic potential drop across the core remains the same, but what is the thing that differs? You see, the flux gets divided into different branches. That is, in a series magnetic circuit, the flux remains constant. Okay, the value of flux is same. But whereas in a parallel magnetic circuit, the value of flux may vary, but the potential drop produced by the flux remains constant. Right? So that is known as a parallel magnetic circuit. So here you see this is the diagram of a parallel magnetic circuit, and this is the central limb, and to this central limb we have a winding. Okay, we have a winding and a current of I amps flows through it. Now the equivalent circuit for this core is drawn below. You see here this is the flux pi produced, right, due to this N into I, and the flux produced gets divided into two, and here it gets divided as pi 1 and pi 2, right? So when you draw the equivalent circuit here, you see, so for this magnetic circuit, here we have a N into I. What is this? This is the reason for producing our flux, right? So here F, this is represented by F, right? So F is nothing but N into I here. So F, and here to this limb, okay, this path will have one resistance that is represented as RC. Since this is a central limb, here we are representing it as C. And here we have this part, the resistance value is R2 and the resistance of this part is R1. So here we are writing it as R2, R1, and the respective fluxes flowing are pi1 and pi2. They are different. And again we are just simplifying this equivalent circuit. Since these two resistors are parallel, I am making it into a single equivalent resistance. So here it is R1 R2 divided by R1 plus R2. So this is our final circuit here. So from this final circuit, what is the value of reluctance here? Here we have these two reluctances in series. So the total reluctance is, we can simply add it, right? RC plus R1 parallel with R2, which is nothing but RC plus R1 R2 divided by R1 plus R2, right? And what is the value of flux? Flux is nothing but mm of my reluctance. So this mmf is given by N into I divided by reluctance here. So we know the value of reluctance, so just substitute the values here, and this is the value of flux. So here R1, R2 are nothing but reluctances of the two outer limbs, and RC is the reluctance of the central limb, right? And the value of mmf is given by F is equal to Ni. So here Ni is nothing but it is H1L1 plus HClC, which is equal to H2L2 plus HClC. That is, you see when you look back at the diagram, here the value is given by, right? So the value of N into I is nothing but our mmf. So here mmf is nothing but it is the summation of the flux, okay, the flux produced by the central limb as well as the flux produced by any one side, okay. This is common for both the sides. Therefore here the value of F is given by H1L1 plus HClC. We can define it in two ways. Either it is the summation of one limb plus central limb, or it is the summation of another limb and the central limb, right? So here you see the mmf in the central limb will cause magnetic potential drop, okay, HClC plus H1L1 and HClC plus H2L2, right? So from this expression, we are framing an expression for pi1 and pi2. So generally pi1 is given by H1L1 by R1. So from this equation, H1L1 can be written as Ni minus HClC, right? And here similarly, the value of H2L2 can be written as Ni minus HClC, right? So this is what I had written here. And this total flux pi is nothing but it is the summation of these two fluxes, pi1 and pi2. So here it is written as pi1 is H1L1 by R1 and pi2 is H2L2 by R2. So when you substitute the values, you see H1L1 by R1 is replaced by this one. So when you substitute these values, you see Ni minus HClC can be commonly taken outside. So the remaining terms are 1 by R1 plus 1 by R2. So this 1 by R1 plus 1 by R2 is nothing but 1 by R equivalent, right? So here comes the end of this parallel magnetic circuit. If you have any doubt, let me know in the comment section. Thank you.